Hello again, welcome to the Academy. This is part of a video series on Calculus 3 topics. This time we'll be talking about divergence and curl. So previously, I talked about this del operator. This looks like an upside down delta. I said how it represents a vector of partial derivatives. And how gradient was gradient of a function, which is del f. And it was a vector field of the first order partial derivatives. But there are a few other things you can do with the del operator. The first thing I'm going to talk about is divergence. So let's keep this in mind. So divergence as the name suggests, is how much a vector field diverges at a given point. In fact, let me just write it right now. The divergence div f of vector field is the dot product of del which is, of course, if f is, let's say, something like L and n, where L and n are a function of x and y, then this would just be the dot product of these two things is just partial derivative of L with respect to x plus partial m with respect to y plus partial n with respect to z. Now this is in Cartesian coordinates. There is another definition of divergence. In fact, the formal definition is coordinate free. The formal definition of divergence says the divergence of f at a point is defined as the limit as v goes to 0 of this expression right here. And this is a surface integral, which I've not talked about yet. But basically, I'm just showing this as a visualization. It's basically, this is the flux of f, of your vector field. Because it measures how much this vector field, so this is a point, this is the surface around it, how much it crosses through the surface. So f dot ds is the end ds, so just integrating at each point how much it crosses through, and actually how much it goes out of the surface. And this is a closed surface. That's why we have this little circle, double integral, and the surface integral really. And so basically we're making v and we're dividing it by this volume of this region. And so what we're doing is we're shrinking it very small and seeing how much the vector field at the limit, how much stuff, if you consider f to be some fluid or something, how much is flowing out of this. And if it's positive, that means things are coming out. And if it's negative, that means things are going in. And if it's 0, that means there's an equal amount going in and going out. Or there's no net flux coming out. So that's sort of the official definition, but there's no, never actually calculate anything using this. You always use this for Cartesian coordinates, and let's do an example that we already know very well. Actually, we can even just do it in 2 dimensions. Consider the function x, y, vector field x, y, which we already know what it looks like. Just arrows coming out. So divergence is just going to be, well, the partial derivative of x with respect to x is just 1, plus the partial derivative of y with respect to y, which is 1. 1 plus 1 is 2. So divergence is 2, in fact, at every point here. And you can see that it is, in fact, diverging everywhere. You go here, there's bigger arrows coming out than are coming in. So everywhere is just expansion. So if this was a fluid, everywhere would be a source. Because positive values are for a source. That's where a fluid is coming out. And it's supposed to sink where things get sucked in. That would be negative divergence. There is no convergence. That's using the del operator to find the divergence by taking the dot product of a vector field. But it's also something that happens when you take the cross product with a vector field, and that's curl. So curl F is, as I said, the cross product. As we know, the cross product is the determinant of this matrix. So there's a partial with respect to x, partial with respect to y, and with respect to z. And just like the cross product, curl is a 3-dimensional thing. This is, we say L, M, and N. So technically, this is, how is it? It's partial n or partial y minus partial m or partial z I plus partial L with respect to z minus, should be partial, what is it, n with respect to x, yes, j plus, let's see, k would be partial m with respect to x minus partial L with respect to y. So this is a vector, as you can see, curl, because of the cross product. And what does it represent? Instead of divergence, which represents how much things flow out or in at a point, this tells you how much things are curling around a point. So if a curl at a point is a vector like this, then things are curling around that point. In fact, following the right-hand rule, if you use your right hand, you point your thumb in the direction of the vector curl, the curl vector, then your fingers will curl in the direction of the curling motion of the vector field. So if you have a curly field, you can think of placing a tiny little wooden thing, for example, it's like a water or a river, and see in which direction and how fast it starts spinning. Now, of course, this is a very long thing to remember. That's why we just use this. But there is, again, a formal definition does not use x, y, and z. It just talks about curl in general, and it says that the normal vector dot product with a curl is the limit as a goes to 0 of this work integral f dot dr over a. So similarly, at a point here, to a point here, and a normal vector n, and we have surrounded this point by some region A that has area A, and then there's a curl, the vector field actually curls around this point. And the curl will look like this by the right-hand rule, and how much it curls by is given by this integral as we integrate around counterclockwise, because this is a counterclockwise motion by the right-hand rule again. So you integrate counterclockwise around here, and you see how much the vector field is actually in the direction of this circular, I guess, curved path. And so you want to shrink this region until you find the limit as you get to that point to actually get the curl at that point. But of course, no one uses the formal definition to actually calculate curl. We just use this. So let's calculate it in an example. Let's use an example in 2 dimensions, although it's really going to be a 3-dimensional thing. So let's say our function is negative y comma x, which we know, and in fact just to make it 3-dimensional, or just make it 0. Doesn't really matter. We know it looks something like this. This is this one that seems to be spinning around. But if we did it in 3 dimensions, it would look like this. And it would be the same everywhere because the z component is 0. So let's calculate the curl. That would be this cross product of f, the del cross f, which is going to be, well, let's see, I, j, k, determinant of this, partial respect of x, y, and z, and then there's negative y, x, 0. So the 0 will simplify the calculation, so I, 0, plus, well, this partial with respect to z of negative y is also 0, and then partial x with respect to x is 1, so it's 1k, so that was I, j, 1k, minus, if we do it the other way, negative y with respect to y is just negative 1k, negative k, plus well, x with respect to z is 0, j, I, and for 0, j as well. So this is 1k minus a negative k, which is 2k, or if you want 0, 0, 2. And that is the vector that looks like this. Color. Go straight up. 2k. So, just like we predicted, really, because we know it curls around, so it just goes like this. In fact, that's everywhere, because this is even bigger as we get further away. So at a point right here, it's going to curl more this way than this way, so the overall curl is going to be counterclockwise again. So everywhere it's curling, it's going to curl the same amount too. And in the k direction, k is the axis of rotation. And then, of course, by the right-hand rule, it's going up, so it's going to curl counterclockwise around that. And there's something interesting about the curl, is that it helps you calculate some things. Earlier I talked about the gradient theorem and vector fields that were conservative. That is, they were path independent, so you could take the integral and it wouldn't matter what the path was, as long as you knew your start and end points. And I said those were gradient fields. So if you have a gradient, then it only matters is it a function f of whatever your point 2 minus your point 1, your starting and end points of your curve. So basically, there's a way to test if a function or if a vector field is the gradient of some function. In fact, you can take the curl, of the gradient of some function. Well, let's do it right now. So the curl of the gradient is going to be ijk, partial with respect to x, partial with respect to y, partial with respect to z, and this is partial f, partial x, partial f, partial y, partial f, partial z. So that would be, so your I component, you calculate I this way, which would be partial with respect to y, partial of f with respect to z, and then partial of y of that. So that would be the second order partial derivative with respect to z first, and then y. Actually, let's do it this way. Plus, let's do j. So j partial with respect to z of the partial of f with respect to x. That's going to be x first, and then z, right? Yes. X and then z. That's I, j. And the k is partial of f with respect to y at first, and then we take it with respect to x. Y, then x, k, minus, let's do it the other way. So here, partial with respect to z, and well, with y first and then with z. So that would be partial second order first with y, then with z, plus I, j would be this one right here. Partial with respect to z first, then x, x, j, and the k would be this. So that would be partial with respect to x, and then y, k. So I want to actually see what this looks like. Let's group them together. So the i's, this is going to be this with respect to z, then y, minus partial with respect to y, then with respect to z. That's I. So the j, which is the y component, is x then z, and then z then x, minus z then x. Minus second order partial with respect to z, and with respect to x. And then this last k component, which is going to be what? Partial second order with respect to y, then x, minus second order partial with respect to x, and then y. But, as I mentioned earlier when we started doing partial derivatives, mixed second order partial derivatives, if the function is continuous, which it is, it's differentiable, we can find the gradient of it, then the mixed second order partial derivatives are the same. So it doesn't matter if I do with z first then y, or with y first and then z. This is really the same thing. So something minus itself is 0. Same thing here. X and then z minus z and then x. Well, these are the same thing. Y and then x, x then y. Doesn't matter. They're the same thing. So this is really the 0 vector. 0, 0, 0. So I'm going to call 0 with a vector sign above it, or just 0. So really, we know that the curl of a gradient is always 0. So gradient never curls. That's why it's also sometimes called irrotational. So if a field is a gradient field, it is also irrotational. It never rotates. It has a 0 curl everywhere. And so if you have a function, so say you're integrating f.dr, and you want to know, well, do I have to actually do it the long way, or can I take the shortcut of this gradient theorem? Is f the gradient of some function? Well, if you take the curl and we find that it's 0, then yes, it is the gradient. But if it's not 0, then it's not the gradient of any function. And so you cannot use the gradient theorem. So it's not irrotational. Just like this one over here that we looked at earlier, kind of erased it. The negative y comma x, we already showed that it was not conservative. It was not a gradient field. And of course we now know that because it does not have 0 curl. It has 2k as the curl. So that was sort of a discussion of the other types of operations that you can do with the del operator, divergence, and curl with vector fields. And thanks for watching, and I'll see you in the next video.